Welcome back. Today's video is about correlation, part of a series on forecasting techniques. Previously, we've looked at the linear equation y equals a plus bx and used regression analysis to calculate numerical values for a and for b to provide us with an equation we can use for forecasting. Correlation examines the strength of that linear relationship, looking at x, the independent variable, and how it impacts on y. We calculate the correlation coefficient r using the formula you can see here. Don't worry, it looks a complicated formula, but if you've previously calculated the regression analysis on a series of data in an exam question, you can use elements of that calculation in the correlation coefficient. Note the resemblance to the top part of the equation. When we look at the calculation of r, that will always be between -1 and 1, with +1 denoting a perfect linear correlation, positive correlation between the two variables, and -1 denoting a negative correlation between the two variables. If r is 0, then there is little relationship between x and y. So we have correlation coefficient as the measure of the degree to which changes in one variable impact on another variable. We can also calculate the coefficient of determination, and that shows the percentage change in the dependent variable that can be explained by a change in the independent variable. That's arrived at by calculating r square. When interpreting the value of the correlation coefficients or the coefficient of determination, care should be taken over how representative is the sample. Is it a valid sample? Does it reflect normal operating procedures or normal operating environments? How big is our sample? If in the instance we're going to look at in a few minutes, there's only 5 pieces of data, that's not going to be a big enough sample to produce any valid statistical analysis. And we've got to be careful about whether the correlation is accidental. It doesn't really have any meaning, it's spurious. Or is there another variable as well as x that will have a significant impact on y? If we look at our example here, we've got some advertising expenditure in one month, and that is followed in the next month by some sales data. So this would be January and that would be February. So advertising in January would have an impact on February's sales. I've already done some basic calculations. We have a table with our columns x, y, x squared, y squared, and xy. These figures have been totaled, all ready to be slotted into the equation. If you look at how the figures have been slotted in, you can see that n equals 5, and then how the data actually would go in. You can see that we have the sum of xy 1366. Spent a bit of time looking at how these figures have been slotted into the equation. Pause the video if necessary. I'd also like you to make sure, using your own calculators, you can come back to the figure R equals 0.99. Always remember to do the computations inside the brackets first, then the next part, which will give you a figure which you can use against the other parts, multiplying the other parts. Do it bit by bit by bit. When we actually do the calculations and we have R equals 0.99, this means, because the value of the coefficient is very close to 1, it means we have a very strong positive linear correlation, and it means that a change in x will produce a measurable change in y. We can then go on to calculate R squared, and when we calculate R squared, this will come to 0.98, and this means that 98% of the changes in sales can be explained by the changes in advertising. The other 2% is caused by other factors. So we know we have a positive linear relationship, and then we know that 98% of the change in sales is explained by advertising from the previous month. Thank you.